So today we're going to talk about some pretty straightforward normal distribution questions. So this is what we're going to solve now. So we have a product. So product overall assembly duration is 3 days with a standard deviation of 1.5 days. So first, let's discuss what we have. So we have an x is normally distributed with a mu with a mean time of 3 days and a standard deviation time of 1.5 days. Okay, so what we're looking for is the chance for the overall assembly time would be less than 5.2 days. So first, let's plot this to get a better understanding of what we're asking, what we're asked about. So let's see. We have basically this is the distribution, right? This is the mean value of 3, and we're interested to see what's the distribution to be less, what's the chance to be less than 5.2 days, right? So effectively, we're interested in this area. You can see that this area is greater than 50%, so we know what to expect. We know we're expecting this to be greater than 50%. So let's see how to approach this. So first, what we need to do, we need to say that we're looking for the probability of x to be less than 5.2. And then we need to convert it to z-score. So z would be less than 5.2 negative 3 minus 3 over 1.5. So this would be probability for z to be less than 1.13. If we do the math for this, this is what we're going to get. So we want to go to find this, the probability for that. So the probability for that would be 1.3, 1.1, and then we need to go to 0.03. So basically, the probability we're looking for is 87.08%. So this would be the answer for the first question. So that is 0.8708, which is 87.08%. Now we're looking for the probability of the assembly time to be greater than 5.31 days. So let's see how this is done. So we can use the same plot for this. We can remove that part, right? And we can say that here we have, I'm going to do a bit of manipulation. Here we have 5.31. And we're interested effectively in this area. Okay. So this is the area we care about. We can see that we're expecting to be less than 50%. So this is how we're going to do this. So we're going to do basically the same thing. We're going to say that we're looking for the probability to be greater than 5.31, which is the probability of z-score to be greater than 5.31, 5.31 minus 3 over 1.5. And we're going to grab that expression, and we're going to go here. And we can see that we're looking for 1.54. So we're looking for the probability of z to be greater than 1.54. And usually there are several kinds of tables, but usually when we're using this z-score table, which is both the less than 50% and both the greater than 50%, we're looking for the probability to be greater than z equals 1.54, and we know that we're expecting the probability to be 1 minus the probability to be of z to be less than 1.54. So this is basically the manipulation we're doing. So we have 1 minus and 1.54 would be 1.5, and we go all the way to 93.82. So basically, we're looking for 1 minus 93.82. And that gives us, I'm going to grab that, that gives us 6.18%. So we have 0.0618 or 6.18%. Now we're looking for what is the duration value that 90% of the distribution is less than. So this is changing a bit what we're looking for. Now we're looking for the value of upon the axis and not the probability within the plot. So we're going to get rid of this, and we're going to get rid of this as well, and this. And what we're going to do, we're going to say that effectively we're looking for 90%, right? So we're looking for this to be 90%. And here we're expecting 10%. And effectively what we need to do, we need to find the relevant z-score for 90%. And from that, we need to extract the relevant x value that'll fit these 90%. So we need to go a bit backward, a bit differently than what we just did. So this is how we're going to approach this. So effectively what we're looking for, we want the z-score of 90%. And we can use the table, and we can look from within the table, and then go outside to the values, the z values at the top and on the left hand side. So let's look for this. So since this is the upper 90%, we're going to look in this table and not in the other one, because the other one approaches values that are less than 50%. Here we're expecting a value that is greater than 50%. So we're going to look for 90%. So we're just going to scan with our eyes, and we can see that we have 1.28. That'll be the value that we're looking for. You see, because here it's 89.97%. So that's very close to 90%. If we want to be even more accurate, we can say that it's 1.282, but you can go as accurate as you like. So we're going to assume this is 1.28. And effectively, we're just doing the reverse work that we just did. So effectively what we're going to do, we're going to look for the x value. So it's going to be x less than x minus 3 over 1.5, and that equals 1.28. So if we want to find the value, so we're going to say that x minus 3 equals 1.28 over, times 1.5, and that gives us eventually, we're going to come up with the x value. So we're going to do this using this, or we're going to do this using pretty straightforward and simple mathematics. And we're going to get that x equals 4.92. So that means that, let's write that down. That means that x equals 4.92. So that means that if the assembly time is 4.92 days, that means that 90% of the work, or 90% of the cases, are less than this value, and 10% of the cases are greater than 4.92 assembly days. So this is how we approach normal distribution. Pretty basic and pretty straightforward questions.